and we touched on it before, but there are a lot of questions coming from these solutions being presented. One of which we touched on before: how are these beta cells self-regulating in terms of their proliferation, their cell life cycles, and metabolic demands, right? If we've all of a sudden got all these brand new beta cells kicking on full cylinders making insulin, do we have the nutrients to make sure that this cell can sustain itself? If it eventually does need immune activation, and we'll learn, in a cell cycle, the immune system is there to kind of clean up the mess, even if it isn't like dangerous. It can be like a maintenance kind of thing to ensure that everything stays on track. If it can't do that, it can't clean up the mess. And if the mess gets to be too big, we're getting into things like tumor permissive environments where it just can't be touched. And this is kind of where that cancer connection comes in. And then the timeline for cell viability and life cycle length. We are all very excited about these technologies because they're hitting the 6-month, the 1-year mark at being viable blood sugar regulating, insulin producing cells. But what about in the future, right? Is this something that we're going to have to come back to and rehash? What are the side effects, the systemic side effects of these technologies? So I wanted to touch just briefly on what the innate and adaptive immunity does, right? They're typically not necessary in a healthy, self-sufficient cell, a well-supplied cell. It's really only when things go awry. And you'll see here in that first bullet, HLA molecules present on almost all cells, right? These are kind of like the little markers that T cells read and are like, are you friend or are you foe? If you're foe, you get knocked out. If you're friend, you're safe. These are situational sentinels to the immune system on whether a cell needs to be addressed, right? Situational is the specific word here, because a cell that's healthy 1 minute might not be healthy the next based on certain factors like redox imbalance. Is this cell accumulating ROS faster than it can clean them up? Is this one cell threatening the livelihood of the group of cells? Are there misfolded proteins? Is there proper nutrient flow and electrolyte flow, fluid balance? Are the cell membranes intact? Is anything spilling out into the open and eliciting an even greater immune response, right? That's where the immune system really comes in handy, even if the cells as a whole are healthy. And touching on that redox balance, oxidative stress within the cell increases the expression of HLA actively. So if a cell is starting to have trouble inside, it starts to kind of send markers like, I think I'm going to be sick. Immune system, can you please take care of me, please? And that's like a good function in a healthy system, right? Cells able to kind of self-regulate themselves to be taken out for the good of the whole. But any small scale hygiene, right? If we've got a perfectly healthy cell that has everything it needs, it doesn't really need T cells, right? Because everything's being processed internally. All of the ROS is being handled. All of the nutrients are moving in and out of the cell membrane. We're good. And then when we go to the kill switch technology, the anti-CD47 technology, what's the success rate, right? Like with this kill switch technology, is it every cell every time? Is this anti-CD47, because CD47 is used by other things in the body as well. Is it messing with anything with that? Is our immune system kind of confused? Coming from people with diabetes, our immune system is already in a state of fatigue as it is. So do we know anything more about this technology? The timeline of it, right? Longevity and the permanence of those transplants. How long does this last? How long do we have before we might need another transplant? I don't know. And this kill switch technology, this anti-CD47, so removing the invisibility cloak or removing the safe signal so that the immune system can recognize it as not safe, it's not new, right? This is actually one of the key movements in the anti-cancer research realm. They're finding ways to eliminate CD47 signaling in cancer cells, but also in specific T cells to ensure that T cells that are specific to certain cancers can remain without being acted upon or broken down. So it's a way of kind of like using fire to fight fire. You're giving T cells the same technology that cancer cells have so that T cells can target cancer. So it's not entirely new. I think it's kind of ironic that it's being used in cancer, and no one's making that connection between cancer and diabetes. But here's a quick little illustration of how that works, right? So to my left, we have this immunoprotected graft of beta cells, all these marked with asterisks. They're healthy cells. They're making insulin. Everything's good. The brown and the red cells, though, they're starting to like hiccup. And again, this could be a random gene mutation. This could be something related to cell resources where it just isn't doing what it needs to. It can't get what it needs to in order to function at a high level. These red arrows are the immune system, and they can't get in to like clean it up. So what happens to a cell that can't do what it needs to, right? It becomes a drain on the system. And if you can't clean the drain, eventually it gets clogged, right? So when you do the anti-CD47, you remove that cloak, right? The gray square is gone, and now everything is kind of exposed to this great big sweeping immune cleaning. And so that kind of clears out not just the brown and the red, but also the green healthy cells. And there's more to this, right? The HIP here, the HIP engineered cells, that refers to hypoimmune protection technology. And that's what it's called, the HLA and the CD47 combination. You can't just clean out the old and the damaged cells. It cleans out everything. And when you clean out everything, but you still need the beta cells that were there, you have to reimplant them, right? So this is a repeating delivery procedure. And there's no selective way to uncloak just the dysfunctional subsets. It's all or nothing.